One of the challenges facing bridge maintenance engineers is the use of non-destructive evaluation and structural health monitoring information. I'm going to present several cases where non-destructive evaluation factored into bridge decision-making related to cracking on steel bridges. And I hope to do this in a bridge preservation context. For our first case, we go back about 30 years to western Kentucky. We have an overpass bridge over an interstate. The bridge is about 10 years old. But we see on the right-hand side here a temporary bench supporting the fascia girder. If we look closer, what we see is that the web of the fascia girder has about been completely severed by a crack. Crack also goes through the horizontal stiffener, and you can see an inspector, and he's using ultrasound trying to find the crack tip so he can cap it with a check hole. Eventually this crack was repaired by lapping with bolted splice plates. But after this was done, the cabinet had a lot of concern because this horizontal stiffener detail was pretty common on deck girder bridges. So they did some studying and determined that the problem occurred in the fabrication shop. In the fabrication shop, to form a sufficiently long stiffener, what they would do is take two pieces of bar stock, butt them up together, and then put a weld on the top and the weld on the bottom, and then they'd weld those to the web of the girder, and then the girder would be put in service, and then problems ensued. And in a fatigue situation, we have, as a result of the welding process, we don't get a complete penetration weld, and we have this piece in here where the pieces of bar stock aren't completely welded together, and this little area acts as a crack starter in a fatigue loading environment. So the inspectors went out in the field and started looking at these details, and here's one that they found. And you can see that the horizontal stiffener has developed a fatigue crack that separated it. The cracks jumped the attachment weld and is working its way into the web before it stopped with the check hole. Now, the inspectors knew that they could find these cases, but they were concerned about the welds that were out there where a crack hadn't nucleated yet. And they had a problem finding these butt welds in the stiffeners because the fab shop ground the reinforcement flush. So to deal with this, they basically shot down the stiffener with ultrasonic shear wave testing, and they were able to readily identify the incomplete penetration welds. And when they did, they preemptively put check holes above and below those locations so any cracks that developed wouldn't jump into the web. When I started looking at these cases, I thought, well, let's describe the activities as a process, and we came up with these 4 steps. And the first step of a highway agency is to identify a problem or concern, then to determine an effective non-destructive method or methods, develop a remedial action, and then apply steps 2 and 3 to all pertinent bridges and structural members. And if they missed one, then there's the likelihood that a crack would develop and jump into the web of a girder. Now we can go back another 20 years, and this is the Silver Bridge at Point Pleasant, West Virginia. It spans the Ohio River between West Virginia and Ohio. The bridge was completed in 1928. It has a main span about 700 feet. It's a I-bar suspension structure, and one of the novel features of it was the fact that the I-bar chains formed part of the upper cord of the truss. But the bridge had several problematic features. The I-bar chains were fracture critical. They were made of a high-strength, low-toughness material. And then the towers were rocker towers, and if one of the chains failed, then the tower would become unstable and it could collapse. Yeah. And unfortunately, that's what happened. In December 15, 1967, we had the worst bridge disaster in the history of the U.S. 61 people were killed. Of course, there was a lot of public outcry, and there was a detailed investigation of the accident. And here you can see the I-bar head that was related to the failure. There's a large crack here on this side of the head, but actually the source of the failure was over here. This was sent to the National Bureau of Standards, and they did failure analysis on the bridge, and they determined that the initial crack was caused by corrosion cracking, and it ran in brittle fracture across the leg of the I-bar head there. And the other thing that they found was the crack size was very small. It was only like 3 to 4 millimeters. And the Bureau of Standards came out with and said that there was no known non-destructive evaluation method that could be used to detect this crack. Yeah. This is the St. Mary's Bridge in West Virginia, crosses the Ohio River into Ohio again. Same basic design, same span, same problematic features, and this bridge was completed within a month of the Silver Bridge. Immediately after that bridge collapsed, this bridge was closed down, and you can see there's a ferry shuttling traffic across the river. This bridge was kept out of service until a decision was made to dismantle it in 1971, excuse me. But there's another bridge. This is the Hercilio Luz Bridge in Brazil. This bridge was actually a predecessor of the two American bridges. It's got a longer span, about 1,000 feet. Same basic fundamental type of design, same problematic features. But unlike the St. Mary's Bridge, this bridge was kept in service an additional 15 years after the collapse of the Silver Bridge. Then it was closed to full vehicular traffic and opened periodically to pedestrians before it was completely shut down in 1991. And this bridge is still standing today. Now, in these cases, of course, we've obviously got a concern the collapse of the Silver Bridge, but we don't have an effective non-destructive evaluation method due to the size and issues with the I-bar cables. There's not really a practical remedial action, so there's no repair that can be performed to safeguard the bridges. So we really get the end point of bridge preservation, either keep it in service or replace it. The Brazilians decided to keep their bridge in service, and West Virginia took the St. Mary's Bridge out of service. Moving a little bit closer to the present, this is the I-794 bridge, Hoan Bridge. It's in Milwaukee, Wisconsin. The main span's an arch structure. This is one of the approach spans. about 200 feet long, supported by 3 10-foot deep girders. And I believe it's under a heavy load in December of 2000. 2 of the girders fractured almost completely. Wisconsin DOT shut the bridge down and replaced the span. And thereafter, there was an investigation. The girders were made out of ASTM A36 steel. Follow-up chemical and mechanical evaluation of the steel, along with Charpy tests, indicated that the steel was acceptable. The other finding of the investigation that was of interest was that these fractures were completely brittle fractures. There wasn't any subcritical crack growth prior to the failures. Now, we can see here, this is a problem area. You can see we've got a vertical stiffener there and a horizontal gusset or shelf plate. And you can see the shelf plate's notched out to accommodate the horizontal stiffener. Apologize, this picture's out of focus, but it's the best one I could find. And you can see we're looking end on at the vertical stiffener here. You can see the fillet weld on one side that attaches the stiffener to the web of the girder. And then we see the shelf plate there. It's got a weld there. And you can see that the 2 welds are in close proximity. Well, the investigators concluded that these welds created a condition of triaxial constraint and high stresses, so when they had a small pop-in crack, it became unstable and ran up and down the girders, causing the fractures. So Wisconsin DOT came in and did some rehabilitation by putting check holes below and above the shelf plate, so any cracks that occurred in this high stress area would be arrested before causing problems. Now, if we look at our process here, we have a problem, not a concern. We don't have an effective non-destructive evaluation method again, but we do have a remedial action, and it can be applied. If you see this particular detail on a fracture critical or maybe a 33 girder bridge, probably want to go in and do that retrofit. And in Kentucky, we have a number of bridges that have that particular type of detail. They call it the Hoan detail. But all the bridges are redundant, and we've never had any fracture problems. So at this point, there hasn't been a need to do any retrofit. But we have a similar situation that I'd like to discuss. This elevation view or drawing of twin bridges on I-75 in southeastern Kentucky in a rural area. 2 bridges are continuous plate girder structures with main span about 200 feet. They're redundant structures with 4 girders per bridge, and they carry 2 lanes of traffic. The bridges were made out of ASTM A36 steel. They were constructed somewhere around the late 1960s, early 1970s. And in 2012, both the north and southbound bridges experienced single fractures, seen here. You can see we've got the vertical stiffener, and then we've got the horizontal stiffener, and we have this narrow gap area there where the welds intersect, giving us that high constraint. See the cracks run up and down below the horizontal stiffener. So our suspect area for crack initiation would be right in here. Cabinet repaired those and went on. And 2 years later, in 2014, they had two similar failures on a single girder line on the northbound bridge. And in this case, you can see the crack growing up, going down, and it's jumped into the lower flange. The Cabinet was going to do a repair on this bridge, and we asked them, well, can you cut out this area in here and give it to us, and let's do some failure analysis on it. So I took it to my failure analyst, and here's an optical picture. You can see here's the horizontal stiffener. There's the end of the fillet weld that's pretty gloppy. And here's the fracture surface in the web. And typically when you see chevron details like this, and there's some above that didn't show up here, they point back towards the source of the failure, which seems to be in this area in here, which meant the crack went this way, shown by the white arrows, and that way downward. So this was the area of concern. We cut the specimen down and stuck it in a scanning electron microscope. In this particular area here, these particular fractures were cleavage fractures indicative of brittle failure. But we have this thumbnail area of interest, and you can see they've got some horizontal lines across there, and these are termed ratcheting marks, and they're a sign of fatigue. And when we amped up the magnification of this to about 1,000, we were able to detect fatigue striations. So this little thumbnail is our critical sized fatigue crack that caused the brittle fracture. It was about 4 millimeters long and about 1.5 millimeters deep. And despite its small size, we knew within an inch or two where the crack would occur, and we thought, well, we went to the cabinet and said, well, we can take a die grinder and clean this area up and come in eddy current and detect it. And if you don't want to do that, you can put check holes above and below the horizontal stiffener. Again, we had a problem. We had what we thought was an effective non-destructive evaluation method, and we also had a remedial action. What did the cabinet do? Well, the cabinet did neither. What they did do is they did frequent visual inspections of the problem areas, and then they, Division of Maintenance, sought to expedite replacement of these two bridges because they're six-laning I-75 near there, and they wanted to replace the bridges with up-to-date structures rather than do expensive repairs. Our next bridge is going to be the I-64 Sherman Minton Bridge. We'll talk about the activities in 2010 probably through 2012. This is a tide arch bridge over the Ohio River between New Albany, Indiana and Louisville, Kentucky. It was one of the first bridges that had welded members out of T1 type steel, and they were used in these fracture critical tie cords here. And somewhere around 1980, they first detected cracks, and we were involved in a consultant inspection back in about 1994-95. We took this picture, shows a crack that's in the web of the box beam at a transition butt weld for the bolted field splices. Crack's about over 2 inches long there. We also did strain gauging, and at that time our strain gauging results indicated that the live stresses were too low and fatigue wasn't going to be an issue. As time went along, the Indiana DOT had some additional concerns, and they determined they were going to perform non-destructive testing and evaluation of the box girders for that problem and other issues. And here you can see a technician doing some inspection on one of these transition butt welds. This is a particular area that was being retrofit during the inspection process. What you have here is a shelf plate, and it's welded onto the inboard web of the tie cord, and you can see that it lapped over the top of this transition butt weld. They were cutting these out, and then they were replacing them with a bolted attachment. And we can go back to September 9th, 2011. I know where I was, and I know where David Steele was, because we were on the bridge. And after they cut one of these loose, they found a small crack here, surface breaking crack. They had a non-destructive testing technician come in, and he did ultrasonic shear wave testing and said that he found that the subsurface of the crack was about 2 inches long. That information got passed up the chain of command, and at some point the Indiana DOT decided to close the bridge to traffic right there. And subsequently, there was a very intense, about month-long period of non-destructive evaluation to finish up inspecting all of these tie cords. And subsequently, the Indiana DOT came up with, there was a multi-state team. They came up with a retrofit that was applied, and the bridge was put back in service in February 2015, or 2012, excuse me. And our next bridge here, this is the I-65 JFK Memorial Bridge. It was built in 1963. It's about 4 miles east of the Sherman Minton Bridge. It crosses the Ohio River between Jeffersonville, Indiana, and Louisville, Kentucky. It's cantilever truss. It has several fracture critical elements, including this upper cord here that's made of the high-strength welded T1 steel. And they had detected cracks on the bridge. And somewhere starting about 1990, 1991, there was some non-destructive testing that was performed. And in this particular example, this is upper cord. They found a large crack. You can see it's highlighted with magnetic particle, or dye-penetrant here, excuse me. And this was in a flange of a H-beam in the upper cord. And it was subsequently repaired with a bolted splice. Thereafter, there was more ongoing non-destructive evaluation, and I think sometime in 1994, there was significant repairs throughout both trusses. I think there were about 90 cracks repaired at 35 of these transition wells using a variety of methods. Just want to contrast the two bridges. And the first area that we see some difference is the identification of the problem or the concern. Indiana DOT was concerned that they'd have an existing crack temperature would drop, fracture toughness would drop, and the crack would become unstable and the tie cord would fracture. And they modeled the critical crack size using fracture mechanics. And they were planning, I think, there was under discussions to close the bridge down sometime when the weather got colder. On the Kentucky Bridge, the consultant cored a lot of the crack areas, sent the cores to a pretty prominent metallurgist, and he provided a report that gave them guidance moving forward. And the other difference occurs down in step 4. The Indiana DOT elected to close the bridge and effect the repairs, and Kentucky repaired their bridge mostly at nighttime under traffic. And so we have this 4-step model we came up with, and it might be useful for you when you're studying the application or non-application of non-destructive evaluation. The most important step, I think, is the first one, where you try to identify a problem and concern and really define that pretty well before moving forward. And the last point would be that the ability to use non-destructive evaluation can be a factor in both repair and bridge replacement decision making. And after that, I'd like to thank you and be willing to take any questions.
Thank you, Ted. Any questions out there? I had one myself on the arresting of the crack or drilling to prevent the crack propagation. I saw you drilled the web of the girder in the cases that you showed there. What was the reason for drilling the web versus drilling the horizontal stiffener or the gusset plate?
Well, I wasn't involved in the decision making of that.
Okay.
There are some other fixes. I know that Federal Highways has a repair where they basically cut into the horizontal stiffener. That was just one of the retrofits. We had another one, a neater one in a way, from Maryland DOT, where they took a hole cutter and went in the backside of the web and cut through and isolated the weld that way.
Sure.
Probably it's a little quicker to effect this type of repair than the Federal Highway repair looks pretty involved. Mm-hmm. So.
Yeah, I was just asking because we've done repairs like that ourselves, the Hoan detail, and we've actually just drilled the gusset plate in the corners where the intersecting welds are, and that we only have to drill 2 holes versus 4 holes all the way around. And that seems to have worked well for us. And then with the horizontal stiffener, we actually just drilled a hole through the horizontal stiffener itself, right along the web. And when we've done that, we've seen that we had a couple of instances anyway. We drilled the hole and the crack popped in the horizontal stiffener immediately as we drilled the hole. So it is an issue, but we don't have many horizontal stiffeners that are in high tension zones. We try to avoid designing them that way, but we had a bridge where aesthetically we put horizontal stiffeners in top and bottom just to make it look nice, so we had to go in and drill those horizontal stiffeners where the butt welds were. So definitely it is a way to prevent the cracking in those details. No other questions there? We're running pretty good on time there, Ed. We want to take a break now and then get into our peer exchange after a break?
Right. First, thank you, Ted. That was a great presentation.